Okay, guys, so sorry it's a bit late. I was just trying to spent a good while trying to get this thing set up. So what we're looking at, I'm going to go through question two. Question two is quite an easy go-to question, um, that we should really be getting close to full marks for. Okay, so the first thing we're saying, so the bicycle helmet is made out of thermoplastic polymer acrylonate acrylonitylbutane. Again, ABS is whatever you know it is for the outer shell, and expanded polystyrene. So again, the outer shell is ABS plastic, the inside is expanded polystyrene. So describe two critical properties to be considered in the selection of expanded polystyrene as a liner. Okay, so again, the likes of expanded polystyrene, so EPS, it's the stuff, your expanded polystyrene, it's the stuff that like if you bought a television, it would come alongside it. Again, if it's being used to package a television, it has to absorb shock. And again, if you bicycle helmet, ideal, because if you fall, you don't want to be hurt. You want to have something that will absorb shock. Again, another thing is the last thing you want to be wearing is something that will give you a creak in your neck, so it is also lightweight. It is very lightweight. Another thing about it is, again, it's quite easy to mold. Okay, so again, quite hard to. I know it's one of the ones we probably didn't go through in as much depth as we should have, but again, we need to think about what if that isn't going to be a bicycle helmet in the leave insert. So what you need to think of is, so it says critical properties of EPS to line the helmet. So you need to think of, because the liner of the helmet, what does it need to do? Okay, straight away, without even looking at EBS, so it needs to be able to absorb shock, it needs to be light, the easy moulding thing, just a Brucey bonus, just a nice little addition. Okay, describe with the aid of a suitable diagram. So again, describe 8 marks, diagram 8 marks, so that's 16 marks, so 8 and 8. The mechanical test to determine the bicycle's helmet to withstand shock or impact. Oh please, I'm afraid the amount of us that put down drew a hardness test is outrageous. You have to do one of the two impact tests. Okay, so I'm going to do both of them here really quickly. Okay, so just so we have revised over both of them. So you have two of them. You have one is IZOD, the other is Sharpie. The first one, IZOD, quite easy. They're not too bad to draw either of them, because you have IZOD. Straight away, IZOD. I know the piece is standing vertical, like an eye. Okay. I haven't drawn a notch on it yet. I want to draw it afterwards in a second. Okay, so it's standing vertical. Again, it is clamped one side. So again, it's gripped at the bottom. I'm coloured in quicker. It is clamped at one side, gripped at the bottom. Okay, we have our strikers coming down here. Again, hits it, sees how tough a material is, how its ability to withstand impact. Okay, now you need to think of which side does the notch belong on. Okay, so for IZOD, it's the side that the striker is coming from. Again, if you did not have a notch on this, it would break anywhere. So you need to put a notch on one side. We're going to put the notch, very big notch, doesn't matter, it's just there so you can see it. There's your notch, okay? So this allows it, so the material will actually break, something like that. So it'll break with the notches because it's narrower there and weaker. Okay, there's a few key things you need to be labeling there. Again, what's shown, but you need to also talk about it. So it's vertically held. One side it's held on, it's clamped on one side. It's clamped on one side. So again, another key thing that everyone left out here is the speed. This is coming down at I. This looks like a 167 joules. That is energy. Okay, so again, the machine looks something like this. How the amount of, there's your piece there. The amount of energy is decided on how high it's swung from. So again, this is 167. The other one, Sharpie, is held much higher because we want to reach 300 there. Okay, so it's all to do with the height that it's held at. That gives you the height, that gives you the power. Okay, another thing you talk about again, how is it measured? It's how far goes this side. Okay, very little difference in the two tests because they're both being hit by the It's a consistent energy. That's, again, if you're testing materials, you're going to stick with Izod or Charpy. You're not going to mix and match between the two. So again, it's all to do with the distance thing goes past it. Again, the further it goes past, the less tough it is, and that is recorded. And that's really it. So that's the Izod. Again, you can draw this exact same thing for Charpy. So again, Charpy, Charpy looks something like this. So CH, once you see H horizontal. Lovely Y. So Charpy, your piece is held horizontal. Like that. CH, because when it's held out horizontal, the horizontal thing, but you could clamp on one side, but the problem is you wouldn't have that much support this side, so it has to be clamped on two sides. And it's not really clamped, it's actually just sort of sitting on a ledge, sitting on something like this. Again, you need to be drawing this. Diagram was worth 8 marks. Just obviously, I don't want to bore you with it, so you want to be drawing on. You want to draw it a bit quicker than, or a bit slower than what I'm drawing. Okay, so again, it's the exact same. It does not matter what shape the striker looks like. Again, it could look like a ball coming like that. But again, maybe don't draw it like that. Draw it something like that looks like the head of a hatchet or something like that. Again, it's key thing they're looking for is a few things that they're always looking for is it horizontal? So this is horizontal. So you need to talk about, so it's horizontal, clamped on two sides. Well, clamped. Again, if you threw down these keywords, it's questionable whether you get any marks, or would you get the full marks. You would get a good bit of marks because you know your stuff, but you need to sort of be putting these into bullet points. Okay, so again, this is coming down at 300 joules. Joules is how you measure energy, and then where's the notch? Again, the problem is if you put the notch here, this is just going to fit into it. The notch is on the far side. Okay, so that is either, if you put down either of those, that was worth 16 marks. That's what let a lot of people down, was they put down the wrong test, or they put down the wrong test. So again, I had to give, you would have got a few attempt marks for putting down the wrong test, but not the full marks. So again, that question there was worth 20 marks. 4 marks for, so 2 marks and 2 marks for describing a critical. So again, it says describe a critical property. So for the likes of that, so again, you could not just go light. So if you said light and absorb shock, again, that you get very little marks. So again, EBS is lightweight because it's full of air. It absorbs shock, which is essential for a cyclist. Again, straight away, either of those things, if you want to talk about the material itself, or you want to talk about its use, it's completely up to you. So the result below shows, see, now we're doing a graph. Might you get a graph? So you have to do a graph, you have to determine Young's modulus and then 0.1%. Okay, so another sheet of paper. A few key things for when it comes to drawing a graph. Look something like that. The stress, what's on the top, flips up to the side. Okay, so the stress goes up here, and then the strain goes here. Strain is all about the stress is the amount of energy that's being put on a strain is the amount that it stretches. Okay, so what you have is, so we're going to divide this into whatever, we'll just say 8 equal parts. Now I know they're not equal, but I just want to point out something here. Okay guys, so that is 8 equal parts, or not even 8, 5. It goes up to 7.5, so you're going to want to go up to 8. So we'll just say for this argument, I'm going to go 1, 2, 3, 4, 5. It'll go the whole way up to 8. Guys, we don't do it like this. The first number thing. So I've done equal parts. The first number is 0.5, 1. Okay, so 0.5, 1. So far we're okay because that's 0. That's 0.5, 0.5. The next one again, 0.5. Then the next one we're looking at is 2.25. That is not right because you've gone, this is 0.5, 0.5, 0.5. Now you're going 0.75. And the next one you're actually going up 1. You're going up to 3.25. So again, they should not be equal distance apart. That's why you always just stick with whole numbers. 1, 2, 3, the whole way up to 8. The exact same goes for your stress. Going the whole way up to roughly 350. I do it up in 50s. Again, it's all to do with approximate values. the result should be something like this. You have a straight line, curve, out. Again, your straight line is your elastic limit to it here. Then you have up here fracture. So your Young's modulus is stress over strain. You studied this, nobody answered that correctly. So stress over strain, you could go up, hit the graph, go across, too inaccurate. Just take stress. So for this, I'm going to go 45 over 0.5. And you have roughly 90. Again, it's very important that you get your unit right. Newtons per millimeter squared. It's actually kilonewtons even. I'll tell you why in a second. Kilonewtons, because that is 1,000. So you need to multiply. It would actually be 90,000 newtons per millimeter squared. Okay, because that's obviously that's multiplied by 1,000. You need to divide that by 1,000. But to keep things easy, we'll just change to kilo. So again, kilo is like kilogram, 1,000 grams and 1,000 grams in a kilogram. And then determine 0.1% proof stress. 0.1% proof stress. You go to 1. You go parallel to your straight line, hit the graph, go across, and get your number there. Again, you have probably a margin of error for about they usually give you a margin of error of about 10. So again, that's parallel to that. Goes up, hits your graph, goes straight across. The roughly should have been closer to about 300. It's usually the 350, 330, something along the lines of that. Okay, and that is how you do your graph question. Straight away, that was another 20-mark question. Because 325 was the answer there. Okay, so again, that's why. So again, we need to sort of practice. You need to be practicing those. Quite an easy one to get, or not an easy one to get, but can be tricky enough. But if you've done a bit of revision, not the worst at all. Part C. So clearly we have a 20-mark. We've had a 20-mark question. We have a 20-mark question. This is going for 10. Okay, so describe. So it says outline 2 benefits. So you'd imagine straight out. So off the bat, it's not going to go 50-50 because one is described, the other is outline. So you're going to say outline will probably be 2 and 2, and the describe is worth 6 marks. So 6 marks. Describe with the end of a diagram. So it's going to be 3 and 3. And outline. So the outline could be 1 mark each. Let me have a look. 2. Okay, so yeah, so it's 8 marks for the description and 1 mark each for benefits. Okay, so it's because it's just outline. So it says eddy currents. Describe it. Okay, so it's quite tricky. So again, it's very important, guys, when it comes to. I'm going to go through the key things you need to know when it comes to material testing. So you have eddy currents. Okay, so you need a diagram, you need a description. First of all, the diagram. So the eddy currents is to do with you have a bar, you have a coil going around it. Oh, I'm not too worried, I'll just draw it like this. What you make, that makes a magnet. It makes a magnet once it's powered. What happens here is you have your piece. Okay, magnetic field is sent through the piece like this. Again, it has to be ferrous though, otherwise, or it can't be ferrous, or else it'll just stick to it. It needs to actually conduct the current. Okay, so you have this here bar, coil. Again, things going through it. Oh my God, we have a flaw here. What happens here is it's actually being pushed around off it like that. So the magnetic field is being distorted. And what happens is, on your normal oscilloscope, should look something like this. So just maintain normal thing. On this, what your oscilloscope, so it's all to do with frequencies, the oscilloscope will flicker like that. So again, it doesn't give us the actual size of the flaw, but it does tell us, look, there's something below. Okay, so your description, a few things need to be mentioned in there. Again, you need to be talking about it. So again, power goes through a core. You have a core with wires, with windings around it. It creates a magnet. The magnetic field passes through the piece. When it's nice and easy, the oscilloscope is. So an oscilloscope is like, it'd be like the thing that measures the heart rate. So it's all to do with frequencies. Okay, so and then so the thing goes through it. Oscilloscope stays as it is. If it meets a flaw, again, there's a distortion in the flow, the current. It shows up again. It does not show us the size of the flaw. It could be huge, could be tiny. Again, usually would. Again, if it's a little tiny distortion, it would be a small flaw. If it's big, but it doesn't show us the shape at all. Okay, and then it says outline 2 benefits of using eddy current testing in the manufacture of railway tracks. That is basically just asking you there. It's just to reword it wrong, words it to try and trick you. Outline the 2 benefits of non-destructive testing. Okay, So again, the thing about it is non-destructive testing is you can use the parts once you're finished. So parts can be used after. So parts. So the likes of a railway track is they can actually be in use. So they can be tested while in use. They can be tested while in use. So again, it locates internal, the all bar ultrasound, internal. Oh jeez, I shouldn't have put a slash. And external flaws. That's one for eddy currents specifically. It's quite safe again compared to you have X-rays, but quite full of radiation, so it's a safe procedure. And they can be the parts can be reused, can be used after testing. Okay, so the parts can be used straight away after testing. So again, like the head of an engine. Things like that. Okay, I'm just going to go through things to look out for when it comes to revision. For question 2, very, very important, few key things. Please pay attention. Okay, question 2, part A is always your destructive testing. D-S-T-R-U-C-T-I-V-E. Finally got there. You have a few things. You have hardness, which is your Vickers. So again, V for Vickers, it looks like this. It's an upside down pyramid really, or is an upside down, not really. Vickers, and you have your Brinell. Brinell B for ball. Okay. The other ones you have your impact testing. You have your IZOD. Again, so I, so the piece is standing up. IZOD 0 for 1, so 167. That's key number to remember there, 167. And then you have a Charpy. Piece is horizontal, and that's 300 joules. Okay, so that's part A. If you know all 4 of those right there, you could get close to full marks in part A, because it's always going to be one of those. Part A is always destructive. Part B is always your graph. So again, it could be the case of drawing a graph. You might have to get the proof stress. Again, part B is always to do with graphs. Just one thing that came up last year, I did go through it, I just want to go through it again, is I had to analyze a graph. They were given 3 different graphs that look like this. Yeah, this is okay. So this is a load extension graph, and then the one that went up like that. Okay, so they had to talk about the properties of each. So this one you can see, this is all to do with how far it extends. And this is the force, or the load, whatever you want to call it. Okay, so this is your normal, this is mild steel. That's your normal that's the one we're so used to looking at. Okay, so you can see this material here had very little force but stretched the site. Okay, so the likes of copper, very, very ductile. Quite a very, very low force needed, again, not very strong. Whereas this one here went and broke. That's the sign of a brittle material. Something, again, I was going to say brass wouldn't be great. The likes of a high carbon steel, or even brass. If you said brass, they'd let you out because it is a high carbon steel. So again, high carbon steel, very, very is very, very brittle. Mild steel is brittle-ish, but just there is a bit of give to it. Okay, so and again you have your, don't forget your Young's modulus is your stress over strain. 0.1% proof stress is just go to 1 straight up. In your load extension graph, you need to divide it by 1,000. Again, if they give you the any sort of dimensions, something like that, means you have to use it somewhere. Okay, I'll go through, guys, when we get back. It's better to talk about it in person. Part C is your non-destructive. A few just to know here. Okay, so you have ones with internal flaws, which is sort of like by eye, so by looking at something visual. And the next one you're looking at is liquid penetration. Where they put a sort of highlighted liquid on the page, and you put it under a UV light, and it shows any surface cracks. Any other surface flaws? Oh, you have your magnetic particle. Might go through a few of these, guys. during the week. Magnetic particle, again, they sprinkle magnetic particles on the surface, put magnet to it, any distortion shows a crack. Then you have your external, so again, oh sugar, this is, oh my god, waking up. That's external, this is internal here, sorry guys. So external meaning on the outside, internal meaning on the inside. Internal, you have your, what we've done today is eddy currents, X-ray, ultrasound. These are both internal and external. And magnetic particle is just below surface also. Okay, and that is part C, usually worth about 18 marks. So all you need to do is, again, that's there's no you're talking about that, you inspect the piece, so you're looking at it, is there a crack on it? 1, 2, 3, 4, 5. Okay, you need to be able to draw those. Liquid penetration doesn't tend to come up because it's so basic. Again, very, very hard to actually draw because it's so simple. It's just a case of drawing just something with a crack in it and just liquid in it. Magnetic particle comes up the very odd time. The main ones that come up are X-ray, ultrasound. I know eddy currents come up in the mock, but the two of these come up so much. A lot of the time what they do is to give to you is to say, name two external tests and 2 internal tests. So you need to be able to know, you need to be able to differentiate between, okay, so eye, obviously we don't have X-ray vision, not able to see inside it. Okay, so it's very, very important that we know the difference between these. Okay guys, I'll go through a few more. If you have anything else you want me to go through, will you please let me know and I can go through it during the week. I want you to have a go at some of these questions, so I don't want to spoil it altogether. Okay guys, thanks.